Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the stereoselective synthesis of beta monocytes, and we have discussed number of schemes how the stereoselective synthesis of beta monocyte is in some cases, in some scheme, how we are getting exclusively or preferentially beta monocyte, because we are discussing this point under the heading that is a synthesis of disaccharide, trisaccharide and the polysaccharide. So whenever we are synthesizing that disaccharide or trisaccharide, all are exclusively in some cases there is a beta selectivity is preferentially, because they are showing as a majority of the compounds exhibit as a biological activity, and therefore we generally our point of discussion or the focusing point of that is to synthesize and before that also we have stereoselective means what, because generally the terms in the organic chemistry using as a chemoselective, regioselective, stereoselective. Chemoselective means which functional group will react. Regioselective means where it will react, and stereoselective means how it will react. In that way, generally these terms are frequently using. So this type of the thing we have discussed in our previous lecture. Right now, today, what we are going to discuss, look at the board over here. What is written? That is a synthesis of 2-deoxy sugar. What does it mean, or how do we define, or how do we come to know what do you mean by the 2-deoxy sugar? To indicate the position, if you know, if you see the pyranose ring, that is a 6-member ring which is always present in the chair conformation, most stable conformation, and as we also know that the bulkier group, whatever hydroxyl groups are there, or they are in a majority of the cases they are the protected one, and only we generally in some schemes the hydroxyl groups are kept free to at a desired position. Desired hydroxyl groups are kept free because there is a glycosylation method, glycosylation process method takes place, and we will get as a formation of, or there is a combination of two sugar unit. One can act as a donor and one can act as an acceptor, and this process is known as a glycosylation, and we are getting as a different type of the disaccharide or even though trisaccharide or tetrasaccharide. So that type of the ultimate objective of this thing. And now the synthesis of 2-deoxy sugar means if you observe the structure of that D-glucose carefully. So here in this particular case, at a 2 position there is not the oxygen atom present. Oxygen atom group is not present, whether it is as we know that it is along with that hydrogen or with the protecting group, it should not present at 2 position, and therefore it is known as a 2-deoxy. D means remove, oxy means oxygen atom from the second, and that sugar unit is known as a 2-deoxy, and why it is necessary to study the synthesis of 2-deoxy sugar, because it shows biological activity, tremendous biological activities are present over there, and that's why the main focus to study the synthesis of 2-deoxy sugar is important or the significant over there. Let's see some introduction regarding that. 2-deoxy and 2,6-dideoxy glycosides are important structural units in many natural products, including anti-tumor drugs. As I already mentioned you that anti-tumor drugs, antibiotics, active against gram-positive bacteria. In a previous lecture we have seen the one of the scheme that shows as a gram-negative bacteria. Now is a gram-positive bacteria. Antibiotics inhibiting platelets, antibiotic inhibiting platelet aggregation drugs used in the treatment of cardiac insufficiency, antiparasitic agents, and whereas the therapeutic effect of these drugs is usually mediated by their glycone part, the glycosidic part is essential for biological activity by regulating the pharmacokinetic properties, not only transport but also molecular recognition. The role of carbohydrates in biologically active natural products has been recently reviewed, and therefore method for the efficient and stereoselective construction of deoxyglycosidic linkage will have useful application in medicinal and bioorganic chemistry by allowing to understand biological mechanisms and elaborate now and less toxic drugs. The lack of stereo directing neighboring groups adjacent to the anomeric center makes 2-deoxyglycoside synthesis a particular challenge. And moreover, the absence of electron withdrawing substituent at C2 makes the glycosidic bond much more acid labile, giving rise to easy hydrolysis or anomerization. Glycals, as we know that the structure of glycals we separately studied, but let us study under these also how glycals are useful in this particular study for the synthesis of 2-deoxy sugar. Glycals soon appeared as ideal precursors, especially for the synthesis of 2-deoxy alpha glycosides, which are thermodynamically more stable than the beta isomers. As we know that alpha isomers and the beta isomers, they are the anomers of each other, they differ at only one configuration, and that type of the isomers are known as anomers. It is a special terms used in the carbohydrate chemistry. The most frequently employed strategy for assessing 2-deoxy beta glycosides uses temporary equatorial blocking groups at C2, which can be removed after glycosylation. These groups should stabilize the glycosidic bond and provide the enantiomer assistance required for good beta selectivity. And the beta, we already learned regarding that beta selectivity in our previous lecture. Electrophilic addition to glycals, mechanistic aspect of application to the synthesis of 2-deoxy glycosides that we are talking about. Addition of an electrophile E plus to a glycal such as protected D-glycol structure number 1 gives a positively charged species which can be viewed as an oxycarbonium ion 2 or 3 in resonance with a cyclic onion ion 4 or 5 respectively. The weight of each structure is highly dependent of the nature of the electrophile and the polarity of the solvent. These are the factors responsible for this. How we can get the 2-deoxy sugar? Let's see, which is represented in a scheme number 1. Let us see the scheme number 1 over here. So now, as we know that the glycol which I am going to represent over here, this is a structure of glycol over here. Here is an oxygen atom, remember here, and here is a double bond present over here, and all other groups we can represent here. OR is that protected hydroxyl group over here, and here also as a OR. And this is nothing but this is a structure of D-glycol. This is a structure of D-glycol, and this you can call it as a structure number 1. Remember, D-glycol. This is a glycol because there is an oxygen atom, allylic type of the group present over here, and that's what is known as this one. And now when this structure, when you add as a electrophile over here, E plus, right? There is a carbon-carbon double bond. So electrophile can attack either this lone pair over here, and this is going to attack at this position, at second position. So what do you get? Before that, we are going to show this type of the intermediate you are going to get. Here the structure will be this one. Suppose as this lone pair like this comes over here, and this is going to attack on this, so that you will get the another structure I am representing over here. Remember here this one. Now there is oxygen double bond, positive charge comes over here, and the electrophile goes over there, and the other part of the group we can represent as a as it is OR. So this is a structure number second. Got it? This is a structure number second, and now this is the double headed arrow represent, indicate this and this structure are interconvertible to each other. So this way, or this is a structure number second, we can show another resonating structure over here. So another possibility over here. So we can, here is a one possible here. Please remember here that electrophile is come from above the plane, and here we can represent the structure like this. There is oxygen atom, then here is a double bond. Now this electrophile is coming from backside, and here is a positive charge, right? This is a structure number 1. The structure number 1 is represented by D-glucol, and when electrophile attack, there are the two possibilities, structure number 2 as well as these electrophile can attack from above face or from below face, from above the plane or below the plane, and therefore we can call it as this is a structure number 3. And here you can represent other part is as it is, here OR, here also as a OR. We are representing that. And when the resonating structure or this intermediate, we can represent like this. Here is a oxygen atom. Here we can show this electrophile, we can show like this. Here is a positive charge attack over there, and now other part there remains as it is OR. Then we can write OR, and you can write as it is OR. Now that electrophile is formed as an intermediate over here. So you can show like this, or we can show other way around also. There is a two possibility we can show over here. So now this is a structure number 4, right? This is a structure number 4, and now after the resonating of this, we can show this here oxygen atom. Then there will be this electrophile can be attacked over there like this, and other part of the structure you can write as it is OR, here also as a OR, and this is nothing but as a structure number 5. Look at here, we are numbering and trying to draw that structure. This is a D-glucol one. We are going to we are studying the synthesis of 2-deoxy sugar. This is a glucol we have taken over here, that is the structure number 1. And when electrophile is easily attacked, there are two possibilities that electrophile can attack from above, that is above plane attack. Here you can show here above plane attack. Here you can show as above plane attack. Above plane attack, above plane attack. Similarly, here you can write that is a below plane attack. Below, it is a below plane attack. Below plane attack, right? Below plane attack we have shown over here. Now this will be this when treated with R-OH, that is a alcohol. What do you get? Because now it is going to attack this way and this get open over here, and again you will get as a chair conformation of this, and the product which we are going to get over here is this one O. Then we can show over here that alkoxy are from this one R dash, and this electrophile will be at this position. Other part of the compound, other groups, they are remains as it is, and this is the structure number 6 alpha D mano. This is a alpha D mano because this is alpha side, alpha D mano. That is the structure number 6, right? This is structure number 5. Now is the structure number 6. In the same way, when you treat this compound with R-OH alcohol, what do you get over here? That is a structure number. Now we make it as a structure here like this. Structure we can get over here like this. This is a structure. Here is a electrophile, and now other part there remains like this OR, OR and OR, this group, and finally here is what we can call it as a positive charge like this maybe, and this is a structure we can call it as this is a what we have to show over here, the structure. This is a structure number 7 over here. This is a structure number 7, that is a 6. This is a structure number 7, and this will be converted into that alcohol is going to attack over there, and now finally you can show this structure this way, right? And here that this is a beta selectivity you are going to get over here, and now at this position there will be a electrophile, then OR, here also as a OR, here also as a OR. Look at this structure, and this structure is nothing but as a beta D gluco, beta D gluco. This one is a beta D gluco, that is the structure number 8. Remember this one. And now the another possibility, when alcohol is added over here R dash OH, what does it give? It gives alpha D gluco, structure number 7, right? Structure number, this is a structure number 8. Now we are going to get as a structure number 8. So here you are going to get again, once again it is going to attack over there. So similarly we will get this type of the structure, but here look at here the OR dash which is coming at axial position, and here this is a electrophile which is present at this is a deoxy, and therefore other part remains as it is OR, here also as a OR, and here also as a OR represent, and this is a structure of alpha D gluco, alpha D gluco, that is the structure number 9 over here. And this is what we can call it as this is a scheme number first. This one is a scheme number first, and which is electrophile promoted addition of electrophile promoted addition of an alcohol to protected D-glucol 1. This is a representation. And now if you see over here at 2 position, there is a electrophile, and this is a what we can call it as a formation of the 2-deoxy sugar. If the addition of an electrophile is made in the presence of an alcohol R-OH, one can easily conceive that the glycosylation stereoselectivity will be dictated by phase selectivity of electrophilic attack, at least if a true onium ion is involved. Trans-diaxial opening of the cyclic ion will occur under assistance by a lone pair of pyranose oxygen atom. An above plane addition should lead to an alpha D manopyranoside, that is which is represented in a structure number 6. Diaxial outcome. Below a plane addition should give a beta D glucopyranoside first as a boat conformer, structure number 7, then flipping to the usual chair conformer, structure number 8, di-equatorial outcome. If a true oxycarbonium ion is involved, one can expect that the stereoselectivity will be governed by the kinetic anomeric effect, leading to a predominant axial stereochemistry at C1, the alpha beta ratio being of course mediated by steric effects. 3 axial substituent can override the stereoelectronic effect. Oxocarbonium ions 2 and 3 lead to alpha D manostructure 6 and alpha D gluco 9 pyranosides respectively. Altogether, 2-deoxy alpha glycopyranosides can be predicted to be more easily attained after replacement of E by hydrogen. Now is a protonation of Glycos. How that protonation can be carried out over here for the synthesis of 2-deoxy Glycos. The acid catalyze addition of an alcohol to an acetylated glycol appears to be the most direct method for the synthesis of 2-deoxy hexapyranosides. However, the acid catalyst has to be carefully chosen in order to avoid the Fourier allelic rearrangement, which is a famous rearrangement. Bullitt et al. Have reported that triphenylphosphine hydrobromide allows mild and high yield protonation, then subsequent glycosylation, and that glycosylation scheme is represented in scheme number 2. Glycals with all equatorial substituent like 3, 4, 6 tri-O-acetyl D-glucol, structure number 10, give mainly alpha glycoside products, so which is represented in a scheme. Let us see that scheme number 2 over here. So let's try to remember these things over here, how we can synthesizing the 2-deoxy sugars. Let's see here scheme number. Once again, that is a glycol I am writing over here. So let's see this one, oxygen atom, then there is a double bond, and other part the group which are protected by acetyl group and which is represented like this. And here, as we know that there is a proton, because we are talking about the protonation of glycals. We are talking about the protonation of glycals. Protonation of glycals. This is the structure of glycals. This is a hydrogen atom which may be as a acidic in nature, and when it is treated with the reagent like triphenylphosphine, PS3P hydrogen bromide, that triphenylphosphine hydrobromide, the 0.05 equivalent in presence of deuterated alcohol. So what they produce? They produce this type of the compound, double bond over here, there is a D, and here you can write hydrogen atom, and other part you can write as it is O AC acetyl group, O acetyl group, and here also as a O acetyl group we get as a deuterated. This is a structure number 10. This will be the structure number 11, and this further converted into, this is a positive charge, this get neutralized. What do you get over here when it is treated with alcohol, suppose as a deuterated rho D, and O R minus still over there, so that is going to acquire over here RO minus, and that is going to attack over there, and you will get this one. So that becomes as a chair conformation right now over here like this. So that is present at axial position over here OR, and there is a deuterium at this position, and now other part acetyl group they remains as it is over here, acetyl, right? And this is nothing but as a structure number 12 which we got over here. So in this way, and this is a scheme number 2. Is a scheme number 2 which is represented over here, that triphenylphosphine hydrobromide promoted addition of a deuterated alcohol to 3,4,6 tri-O-acetyl D-glucol. So that is a structure number here. And now another example, similar example of this type where we can get as a disaccharide. So that is a, let's see that example over here. That is one of the example we are going to consider, and which is a important one as far as exam point of view is concerned. Let's see that structure over here. Oxygen, this we can write like this. This is a glycol. Other part we can show here the protected via acetyl group AC, and then we can show like this. This is a structure number 10 once again, and this will be treated with the one can act as a acceptor, one can act as an donor. Now we can show this is a compound where there is this act as an hydroxyl group, that is a acceptor, and all other part OAC acetyl group, OAC acetyl group, OAC and OAC. This is a structure number 30 you can remember. And then this compound when treated with vein coupling, because this is going to attack here, and so that we are going to get the product like this. NBS is a N-bromosuccinamide. This is we know that the structure of this one, C double bond O, N, here is a Br. This is known as a N-bromosuccinamide. That is the name of this compound, and it is a source of bromine atom, right? And in presence of the CS3CN, methyl cyanide or the nitrile, and at a 5 degrees centigrade temperature is kept, and the percentage, the yield they had got 94% of the yield they have got. And look at this position. So here we can show this one. So at this two position there is no oxygen atom, and therefore it is a deoxy. And now at this position this one, and now you can connect as it is here. This is a group which we can represent over here, OAC acetyl group, once again O acetyl group, here also as a O acetyl group, here also as a O acetyl group. And now here the Br at this position, and now is a O acetyl group, and here also as a O acetyl group. And this is a glycosylation process, and where we got as a disaccharide this 2-deoxy sugar, because at this position there is no oxygen atom, and therefore it is a 2D. And this is a scheme number I think 7 is represented over here, and from that we come to know that N-bromosuccinamide promoted glycosylation of 3,4,6 triacetyl 3-glucose. I think with this we have completed this point. So in the next lecture we will see the next point maybe as a orthogonal strategies in oligosaccharide synthesis. I think with this let us stop today here. Thank you. Have a nice day.